Hello friends, welcome to Joy of Life. So today we are going to look at another medium level problem from Leetcode. The problem number is 146. So it's a LRU cache. So design a data structure that follows the constraint of least recently used or LRU cache. So implement the LRU cache class. So we have to implement this entire class over here, right? So it has a constructor LRU cache int capacity. So it takes the capacity of the cache. Initialize the LRU cache with positive capacity. So you have to give some numbers like 1, 2, 3, 4. It should be positive. It should be greater than 0. And then we have a get function. To get anything from the cache, we need the key, right? So it takes a parameter, which is the key of the value that we should be returning. Return the value of the key if the key exists. Otherwise, return a -1, right? So if the key doesn't exist, then we need to return a -1. The other important function in our cache is a put, right? Wherein you pass both the key and the value. So we'll be getting the key and the value, update the value of the key if the key exists. Otherwise, add key value pair to the cache, right? So if the number of key exceeds the capacity from this operation, evict the least recently used item, right? And also there is a follow-up to it. Could you do it in could you do both the get and put in order of 1? That means a constant time complexity, right? So we are going to look at that, and we are going to see and understand everything in much more details. So if you are new to cache, this video is absolutely for you. If you know what a cache is and you wanted to know how it operates and how we can serve data in order of 1 complexity, the time complexity, how we serve the data, how we put and get the data in order of 1 time complexity, then also this video is absolutely for you. And if you know what a cache is and you have some idea, then do it in a paper and a pen. At least try to solve how the cache works, what would be the data structure that you would be using, and how you would be using in order to design a LRU cache, right? So let's head over to the board and understand the solution, or understand how a cache works in much more details. So a cache is nothing but a key value store, wherein we have the key and the value. We use the key in order to retrieve the item, right? So cache is often used for locally storing some data and which can be accessed very fast. So that's why you perhaps seen in the problem that they have asked for a constant runtime everywhere, because we need a very fast access of the data, and for that we basically use the cache. So whenever you make a network call again and again for the same request and for a particular request, and you anticipate that the response is not going to be changed, it's going to remain the same, in those scenarios you mostly use the cache, right? So let's see some example over here and understand how the same is used, right? I have an application. Let's try to understand the usage of a cache. I'm going to give you a very naive scenario wherein we can use a cache. So suppose you have your application over here, and what you probably do over here is like you store the SSN number, the social security number for the user, or for Indians it will be easy to understand with your Aadhaar number. So every time you give me your SSN number or your Aadhaar number or any number over here, I go to the database to query using the Aadhaar number or the SSN number, and I get your first name, last name, and your address, for example, for the need of our application. Or it might also happen that either we have a database, or I'll put a or over here, or you might call another application which is not yours, maybe which is a government hosted application, wherein you are authorized to get the details for the user. So you pass him the SSN number and it gives you the details. So you pass him the SSN or the Aadhaar number, and what you receive from him is nothing but the first name, last name, and address, right? And there could be several applications where we might have a need like this, right? So what is the problem with this? The basic problem with this is that it requires time, right? The database is not in your own server, right? So you have to make some IO calls. You will go to the database, you are going to query it, and then you are going to get the result, and then you are going to process the result, and so on. There is some network traffic involved in it. Same for the third-party applications. You are going to get the details, and let's say that you have a number which is XYZ, a number, Aadhaar number, or a SSN number. How often these things are going to change? How likely this data is going to change? It's very rare that you are going to change this, right? It's going to be more or less the same thing, right? So what we can do is we can have a cache of our own. So what we can do is we can say that once I will query you, and once I get your data, I will have a cache over here. This is basically a cache. So what I can say is that I can make use of a cache. So I make a query to the database, and when I get a response, I am also going to store them in the cache as an object. There are various strategies of storing. I am not going into that. So as and when I'm getting the response from this guy over here, I'm going to use the response and I'm going to put it in my cache. So next time when you ask me, what I do is I have stored the entry in my cache that this is my key XYZ, and this is his first name, last name, and address. So when I next time get a query for this user to get all these data, what I'll do basically is I'll go and check if XYZ key exists in my cache. I see that yes, it exists. I'm going to return this rather than going to the database or the third-party application again and again, right? What it makes is you tend to serve your request very fast, right? And similarly, you can keep on adding entries like this. So what happens when you store a lot of records is your cache starts growing, right? And you can't store everything that you have, right? There could be billions of people in your country, and you cannot store for each one of them. So what you are going to basically do is you're going to say that, okay, AXY has been used maybe 10 days ago, right? This was used 7 days ago. This was used 5 days ago. This was used 10 seconds ago. So I can say that this is my least recently used entry in my cache, right? So I am going to throw him out when my cache is full. So I say that I am going to store only 4 records. So I have 4 records, and I get a new request to store MNO, right? And I have to throw one of them out. So which one I'll throw out? I will definitely throw out the least recently used. So here AXY is the least recently used, right? So I am going to throw him away and put MNO. And this is called evicting the data from your cache or clearing the data from your cache. There are multiple strategies to do that, but we are going to check on LRU. So this was a little understanding of how your cache works, and then now what we are going to do is we are going to see which data structure will help us to do the get and put in order of ones, right? We need fast, we need to serve data fast, we need to store data fast. Suppose this was taking 15 milliseconds, so the expectation is that my cache will return much faster than this number over here. So here we are going to see how we are using multiple data structure in order to come up with the solution, and we serve the data in constant time. So here let's understand how we are going to implement get and put in the, and our SLA is order of 1 or constant time. So we need to complete both this operation in constant time. So let's put there are some common operations, right? So here are the two common operations that we need to address. One is the eviction. So when we say eviction, we have something called our cache size or capacity, we can say, and we need to evict after that. So let's say the number is 5, just for the simplicity of understanding. And also we have to take care of the least recently item, right? So let's say I have 1, 2, 3, 4, and 5, right? These are my keys, and each one of them had an associated value stored with them, right? And how do we do the get operation in constant time? So I have a key, I need to get the object, and I need to return the object in order of 1 time. So which data structure comes to your mind when we hear that? So for me, I'll say it is nothing but the hash map data structure that comes to my mind. So the map stores a key value pair like our cache, and hash map which ensures that I can return the element in a constant time. So let's put down the operation over here. Get the element from the map using the key, and we know that hash map ensures the order of 1. Since the keys are unique and we are using the hashing technique, we will get the element in order of 1 and constant time, right? So now let's consider this example over here. We have 1, 2, 3, 4, and 5. These are my keys, right? And say 5 is the least recently used, then 4, then 3, then 2, and 1 is the most recently used, right? So how we are going to store that? So now if I get a key over here, new element 6, I see that my cache is full. I need to evict, and I need to evict out 5. So how we are going to deal with that? How do we know that we have to evict 5, right? Which data structure are we going to use in this scenario, right? So what comes to my mind over here is to maintain an order, right? We have to maintain the order. And when we have a ordered kind of things, what comes to my mind is a list, right? In list, we can have the elements in right order, right? And if I create a list wherein I have nodes, we'll come to it in detail. So let's say we have multiple nodes in this list like this. right? So I have a list like this, let's say. So this looks like a linked list, right? Why I chose a linked list? Because I don't know the elements that's going to come, and I have to put that element. A lot of things is associated with that. So what does this list have? So what is the order of this list, right? We can keep things in order. So what I can say is that this is the head, which will have the most recently used, and this guy over here will have least recently used. So whenever I access an element from here, I'm just going to take that element and put that in the front of the list, right? So if you see here that this list and this map over here is storing the same reference, right? And what we are going to do is we have to move elements, shuffle elements in between in the list, right? So for that, what I feel suits best is a doubly linked list. And we will see why we are choosing a doubly linked list over here. So let's create this linked list with 1, 2, 3, 4, and 5, these data, and see why we are choosing a doubly linked list. So these are the nodes, and as you know, in a doubly linked list, what happens is we have two pointers, right? One is a forward pointer, what we call is a next, and we have a prev pointer, so we can come back. So in a normal linked list or a singly linked list, what happens is when you go to 2, you cannot come back to 1, or when you come to 3, you cannot come back to 2. You cannot come back, right? And we will see why we need to come back shortly. And so let's establish the double pointer over here. Let's say we have two nodes over here. One is a head, and we have a marker to the tail, right? So now when you tell me that you want to put a 6 over here in this situation, that a new node has to be entered and our list is full, right? Or our cache is full. What I am going to do is I am going to remove this node, the tail node. Now you think that had it been a singly linked list, how would I update the pointer on the node 4, right? It's not possible for me to update the pointer on node 4. I have to come from the beginning, or I have to maintain the mapping of all my previous nodes, which is again will cost me an extra memory, right? So we are going to have a marker to the head and to the tail, right? And as we know from the above statement, that this is the most recently used and this is the least recently used, right? So when you tell me that you are going to put a new node and my cache is full, how I am going to handle this? I am just going to update this node over here, the last but one node in the list, and set it to null. So 5 is moving off basically, which is the least recently used node. So how we can reach in a singly linked list this pointer? Either we have to store an additional mapping, or we have to traverse all over again to reach the node, right? But in this case, what I can simply say is that I can do a tail.prev, which will take me to this node, and I will set its next, and I am going to set it to null, right? And that's it. I am done over here, right? So this is the reason why we chose a doubly linked list, right? And we see that least recent eviction is something that is taken care of, right? So I'm fine. Now, what about the least recently used? How it's going to help me in the least recently used case? So this eviction that you have just seen, right? What we are doing, are we iterating over the list? If there is a million items in the list, I am going to go over all of them. No, we are not. We know the tail, and we are going to just modify that portion only. So this eviction is also going to cost me order of 1, right? And keep in mind, we have both head and tail marker, and we'll be updating them. Now let's see, this is the condition of our list. So we have seen how we are going to take the insertion into account, right? Now let's understand how we are going to deal with the list recently used. So you wanted to get the element with the value with the key 3. So I will get it from the map, and I will, let's say this is my node over here, right? So you have accessed it, I have returned you back, but now I have to update the same into my map, right? So what I'm going to say is basically node.prev, which means this node over here, dot next is equals to node.next. So basically what I'm doing is I am cutting off this link over here, and instead I am putting this link over here, right? That's how I can take care. And also node.next prev, right? So I'm talking about this link over here. This also I need to disconnect, and I need to put it to node.prev. So basically this link is being associated over here, right? And what we are going to do is we are going to take this node up, and now what we are going to do is we are going to set node.next is equals to head, right? So that means this node over here, now this is my node over here, which is of the value 3. And what I'm going to do next is I'm going to put node.next is equal to head, means node.next is now pointing to this. And what I'm going to say is head.prev is pointing to back to the node. Do keep in mind this is my node. And the next statement over here, I am going to say my head, my new head is my node. So basically that will ensure that I am getting this head thing over here and I am making it point to the same node over here. So all these operations over here is responsible for this least recently used updation, right? So all these operations, if you see that we are not iterating over the list, right? We are just manipulating what we have. So all these operations could be complete in order of 1, right? There was no iteration involved. And that is how our eviction as well as our least recently used has been taken care of in the problem here. So this is the entire algorithm all about. So what we are going to do is we are going to quickly check the code and understand. So let's understand this LRU cache from the code perspective. So the first thing that we needed is the class, the custom class that we have talked about. So here is our class called node. So as mentioned that we are going to store the key and the value as integer. And we need a couple of pointers for the W linked list implementation, that is the prev and the next node. And here we have a default constructor as well for this node class, right? And now let's move over to see what are the instance member variable for this class that we require. So here's what we need. We need the map, which is going to be a hash map implementation for the cache where we have the integer. The return value is an integer, but we are storing a node so that we can keep the instance of this class, right? We need to have an instance member variable for the count. So count basically denotes the number of elements that you currently have in your cache, right? So that we can compare with the capacity and we can work on our eviction. Capacity is something that's constant and that's what we receive in our constructor over here. And so we need to, this is the upper cap for the key value that we are going to store inside our map, right? And then we have the head and the tail for the W linked list, right? So let's look at the constructors. We'll initialize all these variables that we have declared. So the cache is a hash map implementation of integer node with the capacity given. Count is 0 since we have no elements. Capacity is something that we have received, and since there is no list yet, we have the head and tail pointing to null, right? Then we have the get method. So the get method returns a int, so we'll be returning a int, and also we need to return a -1 in case the element is not there, right? So over here what we are going to do is we are going to use the key and look into our map and retrieve the node from the map. If there is a null, if the key is not there, what we are going to do is we are going to return a -1, right? And this node over here, since it has been accessed, it has to come to the front of the linked list, right? So that's why we have this method get node to front. So this node should come to the front of the linked list. And at the end, we are going to return the value, which is nothing but the integer, this integer over here, to our caller, right? So let's look at this function, get node to the front. So this function, what it does is when you pass a node, it gets it to the front, right? So if it is already in the front, that means you are accessing the most recently used node only, which is already in the front. We don't need to do anything. That's why you're checking for node is equals to head, then we don't need to do anything, right? And if you try to access the least recently used node, which is at the tail of the node, what happens in that case? We get the node from that position to the front of the list, right? And what happens because of that is the tail of the list changes. The tail should point to the previous node to the tail, right? Because that tail node has gone to the front. So that's what we have done over here. And then also the pointer manipulation that we have already seen in the board over here. So we are going to do that. So previous nodes, next pointer should point to the next node, and next node's previous pointer, next node's previous pointer should point to the previous element over here, right? And also since we are getting this node to the front of the list, so it does not have a previous, and the head's previous, that's the current head that we have, that's previous should point to this node, and this node's next should point to the head. So we are re-establishing this mapping, this part of the mapping, and we are going to update the head of the linked list to the node that has came to the front, right? So that's all about this get node to the front part. And then the last method that we have is a put method. So what we do is basically in this method is first we check in the map that if the key is already there, in that case we just need to update the value, right? So in that case we are going to fetch the value from the map, and if it is not null or -1 or something like that, we are going to update the value to the past value and get this node to the front again. So we basically leverage the same method, right? And then if that's not the case, that means it's a new entry to the map, it's no more updation. So in that case, what we do is we increment our count, and if our count has exceeded the capacity, we have to get the data out from the tail, right? So if the head is equals to the tail, that means there is only one item, so I make the head null, right? Otherwise, what we do, we remove the item pointed by the tail. So tail.prev.next. So tail's previous pointer is the second last node in the list. I point is next to null. That means I release the tail, and I make the tail point to tail's previous, right? So tail should also come to this node, right? So this is all about the eviction part, when our count is more than the capacity. Otherwise, so once we have taken care of that space, we are going to do this for both the cases. Once we make the space or we have the space, we are going to create a new node with this key and the value. And if head is not equal to null, so initially the head is null, right? In that case, what we are going to do, we are going to put this new node in the front of the linked list. So head.prev is pointing to this new data, and new data.next is my head, right? And also if the tail is also when not established, if tail is null, I'm going to say that tail is my new data. That's again just one node, right? And then I'm going to reset my head to the new data or the new node that I've just created, right? And then I put the key and the value. So I know the key and the value, I put them back into the cache, right? There's one extra. So yeah, this is the solution all about. Let's run this code and see how it goes. It will be fine because I copy pasted. So let's submit and check how's the performance. So it took 13 milliseconds, which is better than 82% of the submission. We are pretty good in terms of memory as well, based on all the submissions. So once again, here the main purpose is to give you the idea on how this entire cache can work, right? So it is one such problems where we leverage multiple data structure in order to ensure that we are giving a constant runtime for all our use cases, right? So for this one over here, for eviction, for least recently used, for get, for put, again putting in the map is also a fun operation, right? So I hope you got the solution over here. You got the concept behind how a cache works, how LRU or the least recently used thing in a cache works, how the eviction is being handled, how the least recently used item is maintained, and how it's been evicted when our cache reaches its capacity. So do let me know what you think about the solution. I hope you got the solution, though it was pretty complex at parts, but concept wise it is pretty clean and simple. The mechanism, how it works, is pretty simple. So do let me know. It would be a pleasure to hear back from you guys. And also, if you have any question with any parts of the solution that we have discussed behind, then just let me know. So yeah, I'll keep this video short over here. I think we have already been overshooted a lot. So yeah, stay home, stay safe. It's been terrible seeing 20,000 cases in Bangalore in a single day. So I request you all to stay home, stay safe, take care of yourself and your family. And yeah, hope to see you guys soon again. Bye bye.